Thank you everyone for checking out this talk. This is a short summary for our paper, How Private Are DP-SGD Implementations. And this is joint work with Lin Chua, Badi Kasi, British Kama, Ravi Kumar, Amar Singha, and Chi Yuan Zhang. And all of us are from Google Research. We are interested in privacy-preserving machine learning algorithms under the notion of differential privacy, which is a mathematically rigorous notion that is widely used in both industry and academia. We say that an algorithm A is epsilon delta differentially private or epsilon delta dp if for all adjacent inputs x and x prime and for all event e, the probability that the event occurs on the output ax is at most e3 epsilon times the same probability on ax prime plus delta. The smaller the epsilon and delta, the more private the algorithm. For the purpose of this short summary, I will not discuss the adjacency notion further. The canonical algorithm for training ML models with DP is the so-called DP-SGD algorithm by Abadi et al. To describe the DP-SGD algorithm, let us recall the SGD, or rather the mini-batch version of SGD algorithm without any privacy guarantee. Here, in the T iteration, we sample a subset ST of examples. We then use backpropagation to compute the gradients of these examples. We then take the average of the gradient and then update the model parameters accordingly. This does not yet satisfy differential privacy. So to achieve DP, the DP-SGD algorithm applies two modifications. First, if a gradient has L2 norm that is too large, then it will perform clipping so that the L2 norm is within a pre-specified bound. Second, after taking the average of this clipped gradient, it also adds noise to the average gradient. These two modifications ensures that the final output satisfies differential privacy. One thing that we have yet to specify in this diagram is how each batch ST is sampled. Indeed, there are multiple choices for us to choose from here. Let us assume for simplicity that we are performing one epoch training, and let B denote the batch size. Perhaps the simplest batch sampler is the deterministic batch sampler, where we just take the next B examples in deterministic order to be our next batch. However, it is known that adding some form of randomness to the batch generation can help improve differential privacy guarantee. So this leads us to the second batch sampler, which we call the shuffle batch sampler, where the examples are first randomly shuffled, and then each of the B consecutive examples form a batch, similar to the deterministic batch sampler. While the shuffle batch sampler is the most commonly used in practice, the privacy analysis of the shuffle batch sampler is quite complicated because there is a correlation between different batches. Due to this, people often consider Poisson batch sampler instead. In the Poisson batch sampler, we assume that each example is included in the batch with probability B over N independently across the examples and across all the batches. So this leads to an interesting situation where it is often the case that shuffle is implemented, but the Poisson batch sampler is used in the privacy analysis with the assumption that the latter closely approximates the former. However, some paper has also expressed a concern that this approximation might be a bad idea. And our main contribution is to formally show that indeed this is a bad idea, where we show that shuffle batch sampler can be much less private than Poisson batch sampler in certain regimes of parameters. In fact, in some cases, we have epsilon that are in different order of magnitude. So the key takeaway here is that we have to be very careful when reporting the privacy parameter of DP-SGD and make sure that the analysis uses the same batch sampler as the implementation. In the paper, we also have more comparison between the deterministic and Poisson and deterministic and shuffle batch samplers. If you want to learn more, please check out our full talk at ICML or our poster, or check out our paper which is on arXiv. Thank you very much.